Hey everybody, how's it going? Today I want to talk about two very fun, very special things. I'd like to talk about the derivative of the inverse function sine of y, and I'd like to talk about the exact same thing for tangent inverse of y. Both of the derivatives of these are things that, for a lot of calculus students, you're taught pretty simply and then are just expected to memorize them. But sometimes you are asked to learn how to derive them, like in our case. So today I'm going to talk briefly about how you can derive the derivatives for both of these equations. Let's start with sine of y. The first couple things that you need to remember to do a derivative like this is the following. Any given behavior in math has an inverse function. For addition, the inverse is subtraction. For multiplication, the inverse is division. And for evaluating a function, the inverse is taking the inverse of that function. Sounds a little complicated, but these are direct opposites of each other. Good way to look at it is if applying a function to one x value, let's say f of x equals y, then you could say f inverse of y equals x. In the same way that 7 times 5 equals 35, and 35 divided by 7 equals 5. The second thing you want to remember is our friend, the vertical line test. If you have a function that looks like this is a function. This can be graphed and modeled as a function. But the second your function does something like this and comes back up around here, and you find that you have two separate points of intersection, that breaks the definition of a function, which suggests that each domain is assigned to a unique element in the range, and it can't be unique if there's 2 points like that. So now that we know this, let's look at the inverse function. Let's look at the function of sine. Let's look at the function for sine, which, if we look at the unit circle and recognize that sine is equivalent to the y value in our function, when we start here at 0, our y value will also be 0. When we come up here to pi over 2, our value will be 1. And then when we come back here to pi, our value will be back down to 0. Then we come to 3 pi over 2, and our value becomes negative y. So we come down here. So this is 1, this is negative 1, this here is our function. And then of course, at 2 pi, it loops back up to 0. Now, this passes the vertical line test, but as I said, the inverse of a function is, of course, the inverse function. So we aren't worried about the vertical line test. We're worried about the horizontal line test to gauge whether or not this is a function, which unfortunately, this function fails the horizontal line test, because if you draw a horizontal line right here, you will see that there are 2 separate points where this line intersects. So instead, what we're going to want to do is we want to find a way to restrict this domain so that we can see every position that our function can go to, but it will not have any non-unique pairings. In this case, we need to limit our function to negative pi over 2 here and pi over 2, which means we are only worried about the values in between these two lines, negative pi over 2 and pi over 2. We're doing something called restricting the domain. And now that our domain is restricted, we can start worrying about the actual arithmetic part of taking an inverse derivative. So let's figure out what exactly it is we're taking the derivative of first. We know that sine of x is equal to y, and inverse sine of x, or excuse me, inverse sine of y is equal to x. That's because inverse sine is the inverse, naturally, of sine. A better way to think of it might be calling this arcsine. Arcsine is the inverse function of sine. And because of the way that inverse functions work, we can also say that sine of inverse sine of y is equal to y. Because right here, we have y, and then an effect is applied to that y, and then an inverse effect is applied to that effect, which puts you right back where you started with this y here. So now we know that sine of inverse sine of y is equal to y. From here, we can take the derivative of both sides, because whatever you do to one side, you'll want to do to the other. And we know that the derivative of y, because it is a single variable, will simply be 1. It's no different than taking the derivative of x. So we can say that sine of inverse sine of y differentiated is equal to 1. Now, what we are looking at with this part of our problem here is chain rule, which, if you'll recall, f evaluated at g of x when differentiated equals f prime of g of x times g prime of x. In this case, our f of x is equal to sine of x, and our g of x is equal to inverse sine of x. So let's go ahead and work that out. The derivative of sine is cosine, evaluated at g of x, which we know is sine inverse sine of x, times g prime of x, which is the derivative of inverse sine of x, which of course we don't know yet. And all of that can be set equal to 1. Now, we're going to come down to this next page, and we're going to say the inverse sine of x, or excuse me, these should all be y's, I'm sorry. The inverse sine of y is equal to 1 divided by the cosine of inverse sine of y. And there's your answer. Of course, it's a very unsimplified answer, so we're going to work to make it a little bit more clear. Let's take a look at the unit circle real quick to figure out what the value of cosine of inverse sine of y is. We are going to take a look right here. Oh my goodness. At our x and y axes, and then we're going to draw a nice orange line to represent our unit circle. We know that at any given point on the unit circle, the radius is going to be the length of 1, and then we can draw this triangle here from that. And there's the triangle that we're working with. Because we are solving for this, we want to figure out what our theta is, and of course, cosine of theta refers to this theta here. So we draw a theta, and our theta equals inverse sine of y. What we also know is that this length here is sine of theta, and this length here is cosine theta. So now we know that our sides, if we draw another triangle here, are 1, and then sine of theta, which we know that theta is inverse sine of y, so sine of inverse sine of y, and then our bottom angle is cosine theta, and again we know our theta is inverse sine of y, so cosine of inverse sine of y. Now, if we take a look at this, you might be able to remember from the beginning of this problem where we said that sine of inverse sine of y is y. So that remains true right here. We can say that sine of inverse sine of y is equal to y. And we know that cosine of sine of inverse sine of y is our denominator right here on our derivative. So let's figure out what cosine of inverse sine of y is. Now, what you can recognize is that this here is a right triangle, which means that this angle, or excuse me, this side length squared plus this side length squared is equal to this side length squared. So we can say that sine of inverse sine of y, which is y squared, plus cosine of inverse sine of y squared equals 1 squared, which is just 1. And then we can say that cosine of inverse sine of y squared equals 1 minus y squared. And then we can say cosine of inverse sine of y is equal to plus or minus the square root of 1 minus y squared. Now, this is interesting because we don't know whether this is going to be plus or minus, but you'll recall that at the beginning of this problem, we restricted our domain from negative pi over 2 to pi over 2. And the interesting thing about negative pi over 2 to pi over 2 on the unit circle is it's this entire area right here. And in this area, cosine is always positive. And that's because at no point in this area is this unit circle line, this orange and blue line here, able to dip to the negative side of the x-axis, which means that we can get rid of that minus and we can say that the derivative of inverse sine of y is equal to 1 over the square root of 1 minus y squared. Just like that. And that's the derivative for sine. Let's talk about the derivative of inverse tangent of x. Now, depending on who you ask, finding the derivative of tangent is actually significantly easier than finding the derivative of secant or sine. We're going to start with the same thing that we started with on this last problem, which is that tangent, oops, wrong sides, which is the tangent of inverse tangent of x equals x, for the exact same reason as last time, because we're doing one thing, then we're doing the opposite of that thing to this third thing, and it's just giving us the third thing. Then we can say, same thing as last time, tangent of inverse tangent of x derived is equal to x derived. Tangent of inverse tangent of x derived is equal to 1. Then we're just going to use chain rule again. So we take our f of x and differentiate it, which we know is secant squared x, which is tangent inverse of x. And then we multiply it by the derivative of this, which is inverse tangent x derived. We can set that equal to 1. And it's going to be the same thing again. Tangent inverse of x prime is equal to secant squared of inverse tangent of x under 1. Sorry, that was not the most intuitive way to do that. So now we just need to look at the unit circle again and figure out the same thing. Let me draw our unit circle in a different color this time. And let's look at our right triangle here. We know that this is 1, this is cosine, and this is sine. But we also know that this line here that extends out down to here is our tangent line. And we know that this whole line here that combines this full red is our secant line. And that's what we're looking for, right? Is secant squared. So we can see that if we take our theta here, which our theta is once again just going to be this number right here. So theta equals inverse tangent of x. And we say tangent theta and 1 if we take this and square them both, it'll give us this squared, because once again, we're looking at a right triangle. So let's draw this out a little bit better. This right triangle here is meant to represent this right triangle here. So we've got 1, and we've got tangent of theta, which we're saying that theta is tangent of inverse tangent of x. And we've got secant squared of inverse tangent of x. Now, once again, because we're doing tangent and then inverse tangent to x, this is just going to equal x. So now we know that x squared plus 1 squared equals secant squared of inverse tangent of x. And that's going to be x squared plus 1, because 1 squared is just 1, equals secant squared of inverse tangent of x. And that's what we have here on the bottom, is secant squared of inverse tangent of x. So we can just say that the derivative of inverse tangent of x equals 1 over x squared plus 1. And those are the only two that we're going to do today. Thank you guys so much. I hope this was helpful.